Okay, in this video what we're going to do is do some Euler method examples and see a way to improve Euler's method. Now I have to admit myself, I was here when I recorded the previous lecture. I don't think it was my best work, so maybe we might just do a quick explainer again of Euler's method, and I'm just gonna kind of say what does it do rather than going too much into the technicalities. So what we have in the background here is some differential equation, which for us in this module is almost certainly, I'll have to be careful, but in general it's going to be the shear as a function of x, or more generally the derivative as a function of x and y. Now certainly for the second assignment it's going to be like this, but I might look to do something like this in the third. Actually, now that I think about it, I can't. Just the way I've set things up. The changes, to closed book assessment means that some of the notes are set up really for open book assessment, but I can actually ask harder questions. But I haven't always included the material, so I can't actually ask this one. Right. So what you have is that you have a differential equation which describes at each point x, so for example at x equal to 0.4, describes the slope of the solution curve at that point. So we're saying we can't actually find v of x, either this is given in terms of data or we can't actually anti-differentiate it. I think example 1 we've something we can't anti-differentiate, and in example 2 we've got the load per unit length given as data rather than a formula. So we will know a starting value. Now how do we know that in the context of a beam is a bit complicated, and I'll just kind of gloss over that, but we have some starting value of the shear. So for example, if this picture doesn't really make sense for shear, I don't think, no it doesn't, but the starting thing here is the starting x value is 0 and the starting, let's call this v value, seems to be 1. So what we do is we travel along, so we've got the exact solution here on top, and the very first step of the Euler method is to find the equation of the tangent to the exact solution, which you can find because you've got a point and you get the slope from the differential equation, and travel along that tangent for a distance h. What you then is you stop and you ask the differential equation again, what is the slope of the solution curve at this point, and you travel along for a distance h along a line of that slope, and you keep stopping, ask what's the slope, go on, stop, ask what's the slope, go on. And you see you get this error, but you have a reasonably good approximation, which is better if the distance that you travel along h is smaller. And so what you end up with is the exact solution at a point, say for example that this would be 1, is approximately a y value, which here would be y of 6. And how do you get the y values? Well, so in terms of what I'm writing in the thing above, the y value here would be the next, and this would be the previous y value if you looked at the y coordinate of that. And the distance between them horizontally is your step size, and the previous slope is, for us actually, be the slope of the exact solution at the previous point, previous slope. Okay, so when you actually do questions here, it's not too difficult, but the questions we're doing are from closed book assessments, so they're kind of easy. Only a little bit of them is done. It'll be up to you in the assignment to explore how we go a bit more. We'll see that. Okay. So let's see. So suppose that if the loading, suppose that the loading on a beam of span L is given by this. Now just for the crack, we might draw this yoke as a load. Now we don't have the span of the beam here, so I'm just going to write it as L load. So the negative exponent, so at x equal to 0, e to the minus 0 squared is e to the 0, which is 1. 20 by 1 is 20, so the load starts at 20. Now what you're going to learn is negative exponentials, and in fact this is a bit more than a negative exponential. If you do the second module the next semester, that negative exponentials go to 0, and if it's a minus x squared it goes to 0 very, very quickly. So it's not a point load at all, but it looks a little bit like a point load at 0 and then going to 1 or going to 0 very, very rapidly. So this is what this load looks like. It says that the shear at 0 is 35. Where that's coming from, I can't, I'm afraid, really answer that. I don't have a pause on this thing, but I could describe a way of kind of finding it, but to be honest, just consider it taken out of thin air. Okay, what have we got? So use a numerical method with a step size of 0.5 to estimate the value of v of 1, the shear at x equal to 1. So we'll draw a little picture down here kind of explaining a little bit what we're doing. But when we actually do the question on the next page, it's going to be easy. The numerical method for us, we're going to do the Euler method. So we're going to have, it's hard for me to think what the shear actually looks like here. Well, we're on, okay, yeah. So here's a shear curve. We know the initial value is 35. So, and what we're doing is we're trying to find the shear at 1 meter. Now, suppose the true solution, oh, God knows. I really don't know. I suppose the true solution looks something like this. Okay, now how long is the beam? That's not actually included here. So what we're going to do is, and this picture isn't ideal, see the horizontal lines pen this, just imagine this isn't actually necessarily 0. So what we're going to do is we're going to travel along the tangent for a distance of 0.5. I might just I probably made it too steep, so maybe I'll adjust it. Something like that, yeah, just cheating a little. So we're going to travel along the tangent up as far as 0.5. We're going to stop, and then we're going to ask what's the slope here, which we can get from this, and we're going to travel along for a distance like that. And this number here, this y value, is our approximation to the solution here. So this is what we're doing. Okay, so that's a picture of what we're doing. If that's a little bit confusing, don't feel too bad. Ultimately, we're going to just be actually using this formula, except with v's rather than y's. Right. So where the role of y is played by v. So let me just write down the formula. Now, of course, the formula previously would have been on an exam paper, but that doesn't really apply now because, you know, it's open book. So the formula you'll be using is that the next value of the shear is equal to the previous value of the shear plus the step size times the previous. So previous means k plus 1 means next, and it means next in terms of the next point. So the points here, x0, x1, x2, which are 0, 0.51. I'll do a little table over here as well. But it's previous slope. And this approximates the true shear at xk plus 1. Okay, so we'll have a little table over here. Yeah, I'm possibly overcomplicating this, but I just want you to kind of appreciate what you're actually doing, because it doesn't really make sense just to do some calculation and not really understand what it's doing. So here's the x value and the shear, and it said the starting x value be of 0. And we're going to v of 1. So we're trying to find out at x equal to 1 in steps of 0.5. So you go from 0 to 0.5 to 1. Okay, and the starting value of the shear is 35. Now where that comes from, I can't be too honest about. Right, now, okay, what's the difference between this question, which was for closed book exam assessment, and what you're going to get? Well, this isn't very accurate, and we're interested in knowing the shear over a full beam. So you'll be asked to go from 0 to, say, whatever, 6 meters, and in much smaller steps, and that means that you'll be using Excel. Okay, so off we go. So the starting value here, okay, so the next value of v, which we call v1, is equal to the previous value. You'll see now it's actually easy. The previous value of v. So we're trying, this is v1 here. I might use some color at the end. Yeah, I'll use some color. So the previous value of here, the previous value to here is 35 plus the step size. Now the step size isn't the x value, it's the difference between the x values which is 0.5, plus the previous slope. Now the slope is got from the differential equation, so the slope is minus 20e to the minus x squared. And the previous slope, it's x squared, so the previous x is 0. And I know that 0 squared is 0, minus 0 is 0, e to the 0 is 1, 20 by 1 is 20. A half by minus 20 is minus 10, so it's 35 minus 10, which is equal to 25. I'll put that in there. Now what does that represent? That represents an approximation to the true value of the shear at 0.5. Now what I've missed out on here is, why don't I just anti-differentiate both sides? You cannot anti-differentiate this. Now it has an antiderivative, but you can't write it down in terms of any formulas you know. So you can differentiate everything, but you can't anti-differentiate everything in terms of what are called elementary functions. So that's why we have to do this numerical technique. Okay, and now we go again. So the next value of v, let's use a different color now, black maybe. v2 is the previous value of v. The previous value of v is 25, plus the step size is 0.5, times the previous slope, which is minus 20, e to the minus x squared, but the previous x is 0.5. Now this is called Euler's method. If you kind of mess it around and use the next value, that will be called forward Euler, and I'll kind of mark it down as wrong, even though it's not, like, you're strictly speaking, you're not doing this, but it's actually kind of valid enough, to be honest. And we'll bang this into the calculator. Now realistically, I don't expect something like this to ever happen in your engineering career. Now we'll do 4 significant figures, 17.21 and shear, so it's kilonewtons. 17.21. So this is the approximation of the shear at 1, and essentially this is your answer. That's it. So a lot of talking there when it could have been done quite easily. Yeah, so the big thing is, as far as I'm concerned, is that when you can't solve the differential equation exactly, there are numerical methods. Now this is the baby method. There's far more complicated methods out there, including ones that can kind of tell you properly what's the reaction at A. But for now, I want you to know that there's some differential equations you can't solve exactly, and so you need numerical methods, and they are out there. Now the next one is one that's far more likely to be realistic in terms of something you'll see. You're not going to have a load given by a formula that you can't anti-differentiate. Like, if you wanted, what you could do is you could fit a curve to this using chapter 1 and anti-differentiate. That'd probably be the normal way. But this second example is probably more realistic. So this is when you got a load, a bespoke load, a once-off load, and you don't have a formula for it. Now you could go off and fit a curve to this if you wanted. Alternatively, you can do this Euler method. So let's chat now and let's do the question. So what we're going to see here is that we don't have a formula for the load per unit length like we did here. So we just have measurements. Okay. And what are we doing? We're starting value of 0. Now this is the load per unit length is 18 and 54. 18 and 54. It's growing quite quickly. Step size of 0.1 to numerically estimate the value at 20 centimeters. So we're going to go jump in 0.1 and then jump another 0.1 to 0.2. Starting value of the shear here is 54. Okay, let's go. So let's use the formula that's up the top of the page. And this time I'll write the approximation slightly somewhere different. So the shear at 0.1 is approximately what we call V1, the next value of V at this point, which is equal to the previous value of V, which is 54, plus the step size, the difference between the x values is 0.1, times the slope. Now the slope is minus the load per unit length, So it should be the previous slope. So it should be the load per unit length minus the load per unit length at the previous point. So minus the load per unit length at 0, and the load per unit length at 0 is 10. And this, if we bang it into the calculator or whatever, is equal to 53 kilonewtons if you want. And we just go one more time using the formula that's up the very top of the page the whole time. The shear at 0.2 is approximately what we might call V2, which is equal to the previous V value, which is 53. I wonder, have you seen something similar in your structural analysis modules? I'm not so sure. Students in previous years have said no. So previous value plus step size times minus the load per unit length at the previous point. The previous point here is 0.1. So the load per unit length of 0.1 is 18, so you get minus 18. And I think if we bang this into the calculator, we get 51.1. And if we want, it's kilonewtons. So 51.1 is our answer. So, 51.2, sorry. So in your second assignment, and perhaps fourth assignment as well, the difference would be that you'll be doing the calculations in Excel. So there'll be way more X values, and there'll probably be possibly a shorter difference between them, because this gets more accurate the smaller the H is. So I suppose that's the other thing to understand. More accurate as the step size gets closer and closer to 0. Okay. So when you do this in your second assignment, there is some help here on how to implement it in Microsoft Excel. So the first way you make this more accurate is you do a smaller step size, but there's another way of doing it, which is, rather than to use tangent lines, use tangent parabolas. So if I look back here, so these little bits are straight lines. You could introduce a bit of curve to these and use tangent parabolas, and that's called the three-term Taylor method, and we're going to do a little bit on that here. So the three-term Taylor method will be probably examined in, possibly examined in assignment 4. Yeah, it will be examined in assignment 4. Okay, so this is, how can you, rather than using straight lines, use a bit of curve, use parabolas. So what you have in a parabola, maybe I'll just write it down here, parabola or quadratic. So we're going to go through the points not with a straight line, but with a bit of curve. Now the thing about these is, just to be clear, this is a line and this is a parabola. So in a parabola, slope changes because it's gone here, and this one's 0 up to almost infinite. And if your slope is changing, that means, if I say the rate of change of slope, and remember slope is dy dx, is non-zero. And how do you find the rate of change of something? How do you find the rate of change of something? You differentiate it. And if you differentiate the first derivative, you're going to have the second derivative. So if you want to use tangent parabolas rather than tangent lines to make your method more accurate, it's going to have to use the second derivative. Okay. Now, if it happens that your load per unit length is given in terms of data, it is possible to estimate the second derivative, but I can't ask you that. It'll only be if the load is given in terms of a formula that you can't anti-differentiate, but of course you will be able to differentiate it. Okay, now we need to just give you the little bit of, I actually will be able to ask you a bit more than I thought, I think, because of this little section here, yeah. So suppose there's a derivative in terms of x and y, so this is an abstract differential equation. How do you find the second derivative is what I'm talking about, because we're going to have to use the second derivative if we're going to have a tangent parabola. So can we find the second derivative in terms of x and y? There is a technique called implicit differentiation, which you would have done last semester, which allows you to do this. So what you implicitly say is, okay, y and this is stuff I'm not going to go into so much, but you can say y is a function of x, so that when you differentiate y squared in this context, can I do a little bit? Maybe I can, maybe I'll leave it off. You see it as y of x all squared, so you'd have a derivative like this. So if you want to differentiate y squared in this let me just write this down. So suppose we have dy dx is equal to x squared plus y squared. So this is a differential equation. Now your job is to find y as a function of x. So this y here is actually a function of x. And this is what's called implicit, so you don't actually have to say it. It's kind of implicitly said by writing down dy dx. And so you want to differentiate this, like if you want to find the second derivative, you'll differentiate both sides. The derivative of x squared is no problem, it's 2x, but differentiating y of x squared, how do you do that? You need implicit differentiation. So the implicit differentiation, well, in this one, just means, okay, the derivative of y is not 1, the derivative of y is dy dx. So as I said from last semester. So this particular one, differentiating y of x all squared, well, using the chain rule, which says if you have an outside and an inside, as you hear, the outside is x squared, the inside is y of x. You differentiate the outside, evaluate the inside, times the derivative of what's inside. Chain rule. So the outside function here is x squared, the derivative of x squared is 2x. And the chain rule says evaluate the inside there is y of x. Now we'll only write y of x once, so when we write the y of x as the inside, we just write y times the derivative of what's inside, and all you can say about the derivative of y is that it's dy dx. And then what you'll do is, in context, the differential equation gives dy dx in terms of x and y, given in terms of x and y already. So in this context, you can write the second derivative in terms of x and y. Okay. So basically what I'm saying is you differentiate both sides. This will just be the second derivative. This will be, say, 2x, and this will be 2y dy dx, and then you replace the dy dx with x squared plus y squared, right? So let's see some more of this theory, or will we leave it till the next lecture? I think we will. Yeah, we'll leave it till the next lecture.